Now, we're going to begin to talk about architecture, molecular architecture, and how it determines properties. And there's really kind of four main topics. One is crystallinity. And amorphous content. What we're going to find is that polymers can be both crystalline and amorphous. In fact, frequently, they're both. Two is what I'm calling the Mur stereochemistry. The Mur is the repeating unit. The repeating unit we'll find can have stereochemistry, and that stereochemistry affects properties, just like the degree of crystallinity or the amount of amorphous material will affect its properties. The third area is what I'm going to call the Mur sequence. Mur sequence. So if I mix Murs, the monomer units, if I mix the monomer units, and depending on how I mix them, I can affect properties. And then finally I'm going to call it the macromolecular structure or topology. And this is how the structure of the polymer changes on a very large scale, much larger than the scale of the monomer. So what do we mean by polymer crystallinity? Well, you might think, well, okay, I got polymer molecules, so I can just stack them together just like a molecular crystal. We talked about that a lot. You talked about that. We looked at that on Wednesday with benzene, right, and naphthalene. They make materials that melt at a certain temperature. They're crystalline. Well, that's not how polymers generally crystallize. What can happen is, if I have this polymer, it's very long, the polymer can decide to fold on itself. In other words, within the molecule, a single molecule itself, it can fold, and the folds form a regular packing. And of course, that's our definition of a crystal. And in fact, here's the picture of what one of these might look like. It folds. They tend to be thin in one dimension. There it is. Thin in one dimension and big in two others. Single molecule, that makes its own crystal. Now, the reality of this is that the real polymer crystal doesn't look like this. It doesn't look like this because what's wrong with this corner? Anybody remember? What's a contributing factor to the shape of a molecule? Well, molecules can bend around, right? Why can't I just fold it on itself? Yeah, the bonds want to be at certain angles. So if I just fold it on itself, I create strain. But since the polymer is one molecule, it has an opportunity. And the opportunity is that instead of just bending around fast, I can go up here and take a couple of loops and then make that pack. I can go down here and take a couple loops and then make that pack. See what I'm doing? I'm getting rid of the strain at the corner. Now, what am I losing? Yeah, I mean, presumably it wants to form this because I get some energy. So I'm getting less energy because I'm forming a smaller crystal. But I'm not having to pay for that strain. So you get the idea? So that a polymer, when it crystallizes, there's some sort of balance between how much is amorphous and how much is crystalline. Less strain. And in fact, they look like this. Dave, could I get the light down? Put it down a little bit. It's really hard. So here's these, over here in the right-hand corner. Oh, this is dying. I think that's dying. Let me get another one. I carry an emergency backup. There we go. Okay, so here's this polymer crystal. See one right there? This is called the lamella. You get lamella because it's not like a 3D crystal. It's more like a 2D crystal. And there's the amorphous gunk in between, and there's another lamella. You can see, and you can see what can happen here is instead of bending around and becoming part of this crystal, that polymer molecule can go over there and be part of that crystal. So these lamella tend to be associated with one another, and they nucleate at a point and then grow outwards in these radiating fashion. So we call these spherulites. And they're very commonly observed in polymers. This tends to be a naturally produced polymer. It's a polyester also. And it's got an interesting story about it. But you can see what happens here is I got this mixture of crystalline and amorphous material. So the degree of crystallinity is going to affect the properties. If I have amorphous material there, oops, there it goes. So degree of crystallinity, we'll call it is sort of the volume of crystal over the total volume. It gets a lot of symbols. I've just chosen this to mean the degree of crystallinity. So if you make a table of sort of properties here. If you have a 0 degree of crystallinity, then these definitely are clear. Right? There's nothing, it's a glass. It's amorphous. They tend to, because it's a glass, they tend to have low toughness. Brittle. With greater than 0, they can mostly be opaque. Not always. They can be clear, but that's only when the crystals are smaller than the wavelength of light, much smaller than the wavelength of light. Sometimes. But generally they're opaque. And they have better mechanical properties, high toughness. High impact resistance, for example. But this also means because there's both amorphous and crystalline material, that means polymers have both a TG and a melting point. Right? Because they're a mixture of a crystalline material and amorphous material. And as you know, amorphous material has a TG. So for PET, polyethylene terephthalate, the melting point is 250 degrees C, but the TG is 76 degrees C. So here's a PET bottle. You've seen these. This is like water bottle. I don't know, my kids got this someplace. This is the PET bottle after the dishwasher. right? Why? Same bottle. Well, I went above the TG. Didn't melt it. But if this bottle has a high fraction of amorphous material, you know, it's probably close, and especially in my dishwasher, it's up there close to 95 degrees C. It's kind of a sterilizing environment. And the viscosity, of course, starts being a liquid, right? And it's going to start to flow. And that's what we mean by, you know, dishwasher safe. Not dishwasher safe.